Hi all, in this video we're going to look at how to determine the area inside an ellipse given by an equation of the form x squared over a squared plus y squared over b squared is equals to 1. So we know to say if we are to sketch that ellipse, it will have a shape. Since we are dealing with a being with x, so we can correctly assume that it has its longest diagonal or its longest um, axis in the horizontal axis. So for such an ellipse, we know to say that a is going to be the coordinates of the vertices. So this is going to be a. So from the origin up to this point, that is a, and up to here, that is negative a. And then up to there, that is b. Up to here, that is minus b. So to get the area for the entire ellipse, we recall first of all that if you had a rectangle like this one with, let's say, the breadth here and the length here, to get the area, it's just a or b. But if, let's say, I wanted to get the area of such a rectangle, like such a shape like this one, instead of getting directly, we can use actually integrals. So to use integrals, we define a small segment or a small section of the ellipse, and we'll call that to say its area. Since it's just a small piece, we'll say its area is a differential area dA. So to get the differential area, when you look at the section we have selected, it's a vertical section. Its thickness, which is in terms of the x-axis, can be taken as dx. Then the height can be taken as y. Then when we look at what y is, the smallest value of y, if we are measuring it from this line, from the x-axis, that's the line y is equals to 0. And at the topmost point, y doesn't have a fixed value. The value of y changes depending on where the section is being selected. So we'll keep it general. The top part will be taken to just say the y value will be y. So that the height here will be y minus 0, which is just y. So that the area will be y multiplying dx. So that the area we're looking at there will be area is equals to the integral of y dx. So for this piece, we're going to first focus on this small section here, just a quarter of the whole lot, knowing that if we can get the area of the whole lot, just multiply to get the area of the whole lot. For now, we're saying focus on this small section here, the quarter. To get the area of the whole thing, just multiply the area you find here by 4. That will give you the area of the whole ellipse. So let's see how the expression for the area of that small piece will be. The area there, in this case, since we're doing this with respect to x, the limits from a to b, these are values of x. So as long as you have dx here, then a and b are values of x. So the smallest value of x for this quarter is 0, and the maximum value of x, notice that it is going to be the vertex there, which is a. So the limits here we're dealing with from 0 to a y dx. So like I pointed out, to get the area of the whole thing, just multiply this by 4 so that you account for all the 4 pieces involved there. So when we multiply this by 4, it will now give us the total area, which is what we're looking for. So it will be 4 and then y dx. Then here we have from 0 to a. But what is y? Since we are integrating this with respect to x, so we need this to be expressed in terms of x. So since we are told to say that this ellipse has this form, we can use this connection between x and y to come up with an expression of y in terms of x. So when we make y subject to the formula, we'll start first by taking the x squared over a squared to the other side, so that now it looks like this. And finally, we'll have y squared, or y is equal to the square root of b squared multiplying 1 minus x squared over a. So of course, b squared can be square rooted so that it just becomes or remains as b. And then under the root, we'll have 1 minus x squared over a. When we substitute, now our area is going to be from 0 to a. And then where we have y, we'll put b root 1 minus x squared over a squared. The a is also squared there. And then we have dx. Okay, so at this point now, the b, of course, will come out of the, there's a 4, remember the 4? So there's that 4 there. So here we have 4b in the integral from 0 to a. Now make this a single fraction, which becomes over a squared. This will be a squared minus x squared. Of course, we are square rooting here, dx. So then we can get the a squared, remove it from the root to be square rooted as well to give us a. So now I have 4b over a, the integral from 0 to a of a squared minus x squared dx. Of course, this is being square rooted. Now at this point, we can perform our integration. Since we have a difference there, a squared minus x squared, to integrate something like this, we'll define x to be equals to a sine theta. This way, dx will be equals to a cos theta d theta. When we make our substitution now, we're going to have 4b over a, the integral, and then where we have a will remain a squared. Where we have x squared, it's going to be a squared sine squared theta. Where we have dx, we put a cos theta d theta. Here I've left out the limits of integration because I've changed my variable to x. So if I'm going to have the limits, those limits should not be showing me values of theta since I've changed from x to theta. So the limit should be showing me values of theta. And of course, to get what the new limits would be, you'd have to just use this. Use that connection between x and theta and just make theta subject, and this will be sine inverse of x over a. So when the upper limit is a, what will be theta? When the limit is now theta, s0 I mean, what will be the new theta? But to avoid doing that, I've just left out the limits. I'll bring the limits back when I change my variable back to x. So for now, I'll just focus on integrating. So here I can factor out the a squared and square root it, giving me just an a. So now I remain with 1 here minus sine squared theta. And then this is a cos theta d theta. This a and this a will cancel out. The other a here comes out, giving us 4ab in the integral of the 1 minus sine squared, that is cos squared. So we have cos squared theta. And then we have this cos squared here, and this cos theta, and that. When you square root cos squared, you get cos. So the cos from here and the cos from here gives us cos squared d theta. So this is the integral that we have to now evaluate. But we recall that to integrate cos squared, we have to use an identity. That is, cos squared is equals to 1 plus cos 2 theta over 2. So using that, we now have 4ab, the integral of the 2 can be factored out, so the 2 just come here, so that we remain in just 1 plus cos 2 theta d theta. The 2 into 4 will leave a 2 only there. When you integrate, the integral of 1 with respect to theta will just be theta. When we integrate cos 2 theta, we get sine 2 theta over 2. So we're done integrating here. So I have integrated, no need for this symbol now since I've integrated. And I will put the limits, so there's no need for me to put the constant of integration. I just need to swap or change my theta back to the original variable. So since we said x was equals to a sine theta, it follows that sine theta is equals to x over a. So now we have what sine theta is, and theta will be equals to sine inverse of x over a. So we now have what to put here, but we need what sine 2 theta is. From the double angle identities, sine 2 theta is equals to 2 sine theta cos theta. So to get the correct answer here, to get the form of this expression, we need cos theta. And to find cos theta, we draw a right angle triangle. If this angle is theta, according to this expression, sine theta is x over a. But sine is equals to opposite, meaning our opposite will be here, which is x. The hypotenuse will be here, which will be a. So using Pythagoras theorem, we get the base here to be the hypotenuse squared, which will be a squared, minus the opposite squared, which will be x squared. Meaning that cos theta will be equals to the adjacent, which is root a squared minus x squared over the hypotenuse, which is a. From here, we see that sine 2 theta will be 2. Where we have sine, we'll put x over a. Where we have cos, we'll put root a squared minus x squared over a. So this is what we end up with. We simplify this a little bit. We get 2x root a squared minus x squared over a squared there. So now we can replace in our expression. So our solution reduced to 2ab, and then we have theta. So where we have theta, remember theta came out as sine inverse of x over a. Plus, now we have the sine 2 theta over 2. So that 2 will bring it outside, so that we just write the sine 2 theta. And sine 2 theta came out as 2x root a squared minus x squared over a squared. So this is what sine 2 theta is. That was everything in terms of the integral. So we'll close this up and bring back the limits of integration. Remember, the smallest value of x was 0. The highest value of x was a. Let's simplify the expression there in the brackets. This will still be sine inverse of x over a. But this side, this 2 and this 2 will cancel out, leaving us with x root of a squared minus x squared over a squared. Then you have 0 to a. Now let's bring in our limits of integration. So this was our original expression. I think our starting variable was x. It all started here. Okay, yes, that was x. Okay, so let's start. So when you put the upper limit first, this is going to be sine inverse of a over a. Since we're saying where there's x, we're putting a, the upper limit, to be a over a, which is 1, plus the second part, since we're putting a here, it will be a squared minus a squared, making the whole thing here to be 0. So we're seeing that after putting the upper limit, we have this expression. Minus, now we're going for the lower limit. When we put the lower limit, which is 0, this becomes sine inverse of 0 over a, which is just 0. And then when you put 0 where there's x, because this is multiplying, the whole lot here becomes 0. Then we have this now. When we get sine inverse of 1, sine inverse of 1 is 90 degrees, but in radians, that is pi over 2. So this will just reduce to pi over 2. Sine inverse of 0 is 0, so this whole lot here will also be 0, leaving us with only this expression. The 2 will cancel with this, giving us 1. so that our area now reduces to pi AB square units. So this becomes our expression for the area inside an ellipse. Alright guys, hope you found this helpful. If you want more solutions, leave a like, let me know in the comment section. And to join the online daily math classes, you can reach me on WhatsApp on the number 0979 38 20 81. Of course, 26. Like that. Alright, we'll see you guys in the next tutorial. Let me know if you'd want to see more problems. Let me know in the comment section. And what would you want to see next? Alright, bye.